All right, hi everyone. Good afternoon. Yeah, and a happy new year to everyone. Hi Shaunak. Hi Anjali. Afternoon Aditi. Afternoon Deepak. Yeah, hi, good afternoon Vrishti. All right, I hope you guys had a good start to the year. Good, great. Now, keeping in mind, आप लोगों का अब मेजर टेस्ट का डेट आप लोगों को अनाउंस कर दिया है? Okay, I'm getting a mixed answer. Some are saying yes, some are saying no. Okay, so maybe हो सकता है बोकारो में अभी तक अनाउंस नहीं किया है. पुणे में अनाउंस कर दिया है. What about Delhi? अच्छा, not yet. All right, all right. हाँ नहीं, tentatively ऐसे mid February is what is being announced, but not sure for all the locations because depending upon how the syllabus is getting completed, there would be a bit change in the schedule. हाँ, अभी 11th और 12th का डिस्टिंक्शन खत्म हो गया है भाई. So yeah, from the school perspective, you guys might be thinking 11th and 12th, but from your competitive exams perspective, दोनों का syllabus आता है, तो it really doesn't matter whether you guys are in class 11th or class 12th. ये सब अभी like silos है 11th and 12th which don't matter to you. All you need to know is that by October this year, we should be targeting to get your syllabus done. Anyways, like I'm sure that you guys got a lot of time to cover up on any backlog that you had. Last week we were not able to take a class, so I'm assuming that that buffer helped you in overcoming any backlogs that you had in your homework, and you were able to do your homework till this part. This was the latest homework that I had shared with you last class. So this is something that we will be doing today. Like we will be discussing, if not all, but some part of it. However, I'll not start the discussion with this. We will keep it towards the later part and then go through your doubts. Now, as a quick recap of what was done in the last class. So if I remember, we had finished off the part of thermochemistry and we started with the second law of thermodynamics. And we discussed second law of thermodynamics from the point of view of entropy, right? Then after discussing that, we worked on calculation of change in entropy, like after studying what was the basic definition, and I had asked you to then focus on the change in entropy. We got that result for change in entropy of system and surrounding for reversible and irreversible processes. And I did explain the spontaneity bit, like what is meant by the condition of spontaneity using this example of phase transformation. And then towards the end, we were applying second law of thermodynamics or doing in fact second law calculations with the ideal gas. So I hope you remember how we arrived at this result of change in entropy of an ideal gas. Right? We did a proof also However, even if you don't remember the proof, you should at least be able to remember how we, or what is the result for change in entropy of an ideal gas, and correspondingly what would be the change in the entropy of the surrounding, right? And then I had asked you to fill this table up. So did you guys get a chance to go through this? Like already वैसे तो मैंने आपको fill करके दे दिया था, like I had done this task for you, but I hope you validated your understanding with this. Is this table something that everyone understands? ये हम लोगों ने टेबल फिलअप किया था फॉर आइडियल गैस. वी डिस्कस डिफरेंट प्रोसेसेस एंड उन प्रोसेसेस के लिए we went about doing the calculation of change in entropy of system and change in entropy of surroundings. So we did isochoric, isobaric, isothermal and adiabatic processes. If you do not remember, तो हम एक बार क्विकली इसके थ्रू वापस से चले जाते हैं. Do you remember this result? The change in entropy of an ideal gas. This was the, you can say, mother result or summary result for change in entropy of an ideal gas when it is taken from one state to another state, right? And now let's say if I was talking about an isochoric process. So isochoric process में क्या हो जाएगा? V2 V1 सेम रहेगा and ln of 1 क्या होता है? 0. So what will be my delta S of the system? Delta S of the ideal gas. It will be simply NCV ln T2 by T1. Right. So that is what we had done in this table of ours. That okay, if the ideal gas was going through an isochoric process, right, then delta S system, right, for which the core formula was NCV ln T2 by T1 plus NR ln V2 by V1. This was the core formula. So in case of isochoric process, it simplifies to NCV ln T2 by T1. Or if you wanted, you could have done this or got this answer via the basic formula that ds is integral dq by t. Constant volume processes में dq क्या होता है? Do you remember what was dq in constant volume processes for an ideal gas? It was equal to du, of course. So can we write it as NCV dt? Correct. Can I write this as NCV dt? And then if I do the integration, n और cv तो बाहर आ जाएंगे इंटीग्रल के. Am I getting the same answer? NCV ln T2 by T1. वैसे भी आप कर सकते हो. Correct. Now, for irreversible processes, I am putting the same answer of delta S. It is the same answer NCV ln T2 by T1. Why did I do that? Can anyone tell me? Why did I put the same answer for irreversible processes? Reversible isochoric के लिए it was NCV ln T2 by T1. Irreversible के लिए correct. I had put the same answer because entropy is a state function. Heat nahi shresht, entropy. Entropy is the state function. So be it reversible or irreversible process, my change in entropy was same if I was going from some given initial state to some final initial state. ऑलराइट, नाउ डू यू रिमेंबर डेल्टा एस सराउंडिंग हम लोग कैसे निकालते थे? हाउ डिड वी कम अप विद डेल्टा एस सराउंडिंग? तो यहां पर हम लोगों ने सीखा था दैट डेल्टा एस सराउंडिंग will be minus delta S system for reversible processes, and for irreversible processes, what did we study? The delta S surrounding will be minus Q system by T surrounding. Right? This was our result for irreversible processes. Right? हाँ, correct. So यहाँ पर अब आप notice करना, for reversible process, for reversible isochoric, my delta S surrounding, I calculated or computed the value as the same, minus NCV ln T2 by T1. And for irreversible processes, it was minus Q upon T surrounding. What was Q? In case of isochoric process, it was NCV delta T, or NCV T2 minus T1. Right? All right. Then for isobaric processes, right? Isobaric processes के लिए, how do I get my result of delta S system? Right? Either I use this formula that delta S was NCP ln T2 by T1 plus NR ln P1 by P2, and then put this to 0 because it is an isobaric process, and get my answer as NCP ln T2 by T1. Right? Or what is the other way in which I can get this as an answer? I could use the formula, the fundamental formula, that ds was integral dq by t, and in case of isobaric processes, dq is ncp dt. Correct? And I would have got the answer that in case of isobaric processes, the change in entropy is ncp ln t2 by t1. Right? Having understood this, अब आपको ये बाकी वाला पार्ट तो समझ में आ ही जाएगा, that irreversible में system का change of entropy वही लिखेंगे, whereas for surrounding in reversible it will be minus delta S system, that is minus ncp ln t2 by t1, and in case of irreversible it will be minus q system by t surrounding. And what will be q system in this case? ncp delta t. Right? Isobaric समझ में आया? All right, great. Then isothermal में, let's say if you were doing isothermal process, then how would I get delta S system? I can either use the ideal gas का formula NCV ln T2 by T1 plus NR ln V2 by V1, right? And then put this to 0 because isothermal hai, temperature is not changing. So ln 1 is 0, and hence I got my answer as NR ln V2 by V1. Either I can do this, or what else can I do? I can use the fundamental formula also if I like. What was the fundamental formula? ds is equal to integral dq by t, and because this is isothermal, ठीक है, तो यहाँ पर आप नोटिस करना t कांस्टेंट है तो मैं t को इंटीग्रल के बाहर निकाल लूंगा, ठीक है, dq को इंटीग्रेट करूंगा तो ये क्या बन जाएगा, q by t, राइट, एंड q will be minus w for isothermal because isothermal में delta u 0 होता है, राइट, एंड डू यू रिमेंबर रिवर्सिबल isothermal वर्क कितना होता था, माइनस nRT ln v2 by v1. रिवर्सिबल isothermal वर्क अगर आपको याद हो तो I get my answer as minus nr, or in fact minus minus का I got the answer as plus nr ln v2 by v1. ऐसे भी डिराइव कर सकते हो। समझ में आया ये वाला भी? ग्रेट। हाँ हाँ, मतलब आई होप दिस इज हेल्पिंग यू इन रिवाइजिंग द प्रीवियस कॉन्सेप्ट्स ऑफ थर्मोडायनेमिक्स, क्योंकि एक्चुअली थर्मोडायनेमिक्स का फर्स्ट लॉ करने के बाद में थर्मोकेमिस्ट्री पे आते हैं और फिर से सेकंड लॉ कराते हैं, तो कई बार बच्चे भूल जाते हैं पुराना क्या कराया था। तो आई होप दिस इज हेल्पिंग यू रिकैप ऑल ऑफ दैट। ठीक है। एंड देन अगेन डेल्टा एस फॉर सिस्टम इन केस ऑफ irreversible will be the same, nr ln v2 by v1. For surrounding, in case of reversible it will be minus delta S system, and in case of irreversible it will be minus q system upon t surrounding, and q system will be what? Minus q will be equal to work done in case of isothermal processes. Isothermal में delta u zero होता है, और वर्क कितना हो जाता है irreversible में? Irreversible में it is minus p external delta v. Correct? So from here you got the answer. ठीक है, ग्रेट। अच्छा, अब थोड़ा सा इंटरेस्टिंग है। वाई थोड़ा सा इंटरेस्टिंग है? नाउ नोटिस करना, वी आर कमिंग टू एडियाबैटिक। सबसे पहले रिवर्सिबल पे फोकस कर लेते हैं। चलो, रिवर्सिबल एडियाबैटिक में वी आर गोइंग फ्रॉम सम P1 V1 T1 to some P2 V2 T2, and now my this formula, that is ds is equal to dq by t, right? तो एडियाबैटिक प्रोसेस में in fact I had been writing the formula incompletely. ds was equal to dq reversible upon t, right? तो रिवर्सिबल एडियाबैटिक प्रोसेस में ये dq क्या हो जाएगा? 0, and as a consequence my ds was 0. The change in entropy for system was 0. This was from this basic formula. However, if you are of this opinion, that is also a word that is used in case the entropy change of the system is 0, then we use the word isoentropic, right? In fact, I'll put it over as a note over here. ठीक है, क्या नोट रहेगा ये? Isoentropic means delta S system is equal to 0, मतलब एंट्रोपी चेंज नहीं हो रही है सिस्टम की। ठीक है। Anyways, this was based on that fundamental formula. I had come to this conclusion कि 0 होगा. Can you come to a conclusion based on this formula also, that why this will be equal to 0? Why this left hand side is equal to 0? Can anyone tell me how to work on this? नहीं, Q0 तो मैंने अभी यूज कर लिया ना तृप्ति। हाँ, राइट श्रेष्ठ, राइट शौनक, good. So another way of thinking or coming to this answer is in this way. Can I write CV as R upon gamma minus 1? Can I do that? Of course I can do that. Can I take NR common? In fact, let me take NR gamma minus 1 as common. तो ये क्या बच जाएगा? ln T2 by T1 plus gamma minus 1 times ln V2 by V1. Can I combine these lns? तो ये क्या हो जाएगा? T2 V2 की पावर गामा माइनस 1 अपॉन T1 V1 की पावर गामा माइनस 1. Now, do you remember that for adiabatic reversible processes, T V की power gamma minus 1 was constant, and hence this becomes ln 1, which makes this 0. Right? So I can use that also to explain that why change in entropy of a reversible adiabatic process is 0. Now, this is something which can also then help me understand that why adiabatic irreversible processes delta S system is not equal to 0 but greater than 0. ठीक है कैसे अब आप यहाँ पे नोटिस करना because in our initial discussions I had told you about that between two states there can be only one adiabatic link. It can be reversible or irreversible. So अगर मैं P1 V1 T1 से P2 V2 T2 जा रहा हूँ in an adiabatic reversible manner, then I can never go in an adiabatic irreversible manner. Even if I try to do something forcefully, like I go from the same initial state and say कि नहीं volume तो मैं V2 पर ही जाऊंगा, then you remember that I had told you that I will end up at P2 dash and T2 dash, and this was because both these processes follow different process equations. यहाँ पर PV raised to the power of gamma constant था, यहाँ पर वैसा कोई process equation नहीं था. सो इनएविटेबली अब यहाँ पर नोटिस करना मेरा फॉर्मूला जो हो गया है डेल्टा एस का, इट वुड बी एन सी वी लॉन टी टू डैश बाई टी वन प्लस एन आर लॉन वी टू बाई वी वन. दैट विल बी माई फॉर्मूला. यहाँ पे टी टू की जगह टी टू डैश आ जाएगा. ठीक है. एंड वाई इज दिस टर्म ग्रेटर देन जीरो? बिकॉज delta S system plus delta S surrounding has to be greater than 0. Delta S universe has to be greater than 0 for an irreversible process. अब सराउंडिंग का जो एंट्रोपी चेंज है वो तो 0 रहेगा क्योंकि सराउंडिंग का एंट्रोपी चेंज क्या था? माइनस क्यू सिस्टम बाई टी सराउंडिंग. And in case of adiabatic processes, that is equal to 0. Right? So we get the answer as minus, we get the answer as that delta S universe is greater than 0, and that is why this entropy change for an adiabatic irreversible process will be greater than 0. समझ में आया ये? टिश्यू आप इधर नोटिस करो ना, टी बी की पावर गामा माइनस वन इज कांस्टेंट का मतलब क्या रहेगा? टी वन वी वन की पावर गामा माइनस वन इज इक्वल टू टी टू वी टू की पावर गामा माइनस वन. तो why would this ln 1 become 0? ठीक है. अच्छा, now that you understand this, can I add on to something which I had skipped while we were discussing the graphs? What was that? Do you remember? हम लोगों ने आइसोकोरिक, आइसोबेरिक एंड आइसोथर्मल, राइट, इनके ग्राफ्स बनाए थे. बट मैंने एडियाबैटिक के ग्राफ्स नहीं बनाए थे. नाउ आई कैन ड्रॉ दोज ग्राफ्स ऑल्सो फॉर यू. ठीक है, किस तरीके से आप नोटिस करना है यहाँ पर. From these two conclusions, ठीक है, from these two can I conclude that T2 dash is greater than T2? Can I do that? From these two results, adiabatic reversible में entropy change NCV ln T2 by T1 plus NR ln V2 by V1 is equal to 0, and adiabatic irreversible में NCV ln T2 dash by T1 plus NR ln V2 by V1 greater than 0. So if I subtract one from the other, ये तो cancel out हो ही जाएगा. Like I will be able to cancel this out, and then if I take NCV common, I can get this result that T2 dash is greater than T2, right? So based on this, can I make a couple of statements? Let me see if you can answer them. So यहाँ पे notice करना. In case of adiabatic expansion, say from V1 to V2, what happens to the gas? Does it cool down or does it heats up? दीपक, क्या आंसर कर रहे हो तुम? एडियाबैटिक एक्सपेंशन में क्या होता है? Q तो जीरो रहेगा, एक्सपेंशन हो रहा है मतलब वर्क नेगेटिव है, राइट? तो डेल्टा यू भी नेगेटिव हो गया ना, मतलब टेम्परेचर भी डिक्रीज हो जाएगा. परफेक्ट. सो द गैस कूल्स डाउन. ग्रेट. नाउ इफ आई ask you a question, or if I make a subsequent statement, it cools down more in case of adiabatic dash as compared to adiabatic dash. What will be your conclusion? You have to fill these fill-ups with reversible and irreversible. करेक्ट. अभी जैसे मैंने आपको बताया, यहाँ पे नोटिस करना, ये टेम्परेचर का स्केल है, राइट? दिस इज टेम्परेचर का स्केल, एंड से वी वर एट अ टेम्परेचर T1 एंड कूलिंग करने पर क्या हो रहा है, एज इन एडियाबैटिक एक्सपेंशन करने पे कूल हो रहा है, तो वी आर गेटिंग अ लोअर टेम्परेचर. दिस विल बी T2 and this should be T2 dash. Why? Because अभी I have just proven to you that T2 dash is greater than T1. तो कहाँ पे ज़्यादा cooling हो रही है? It is getting cooled down more in case of reversible as compared to irreversible. Great. अच्छा, let me do some copy paste. थोड़ा सा modification आ जाएगा. Let's say if we were doing adiabatic compression, in case of adiabatic compression, what happens to the gas? the gas heats up, right? Now it heats up more in case of irreversible as compared to reversible. कैसे? अब आप यहाँ पे नोटिस करो, this would be T1, this would be T2 and this will be T2 dash. समझ में आया? So let's say if I was to also show this to you, ये तो मैंने क्या अंग्रेजी में like statements के फॉर्म में आपको दिखाया, but if I was to put it in terms of a graph, ठीक है, यहाँ पे नोटिस करना, for same change in volume, ठीक है, let's say if I was to put this up in form of a graph, तो ये कैसा दिखेगा? नोटिस करना, so say this is the initial P versus V graph है, this is P1 V1, this is our initial condition, and ठीक है, this is I am talking about for the same change in volume, and let's say I even for same expansion in volume, right? हम लोग V1 से V2 जा रहे हैं. So this would have been, say, the final point of reversible graph. ठीक है? Where would be the final point? मेरा volume change यही है. ठीक है? Volume change मैं V1 से V2 ही जा रहा हूँ, starting with the same initial point. Where would my final be for the irreversible graph? Will it be ऊपर or will it be नीचे? Same volume change I am undergoing V1 से V2, right? Since T2 dash is greater than T2, so can I say P2 dash is greater than P2? Because V2 is something that we are keeping same, like for the same change in volume. So what should be my answer? Correct. This will be my F final point for irreversible. Say this is some F dash. समझ में आया? I will not, of course, you remember that I don't draw irreversible के graphs. I can only plot the initial and the final point. ठीक है? Maybe now you can try. Let me pose a question for you guys. Okay. Let me do it for compression. For same compression in volume. What do I mean by compression? अब ये मेरा initial रहेगा. Say this is my initial. This is my V1. This is my P1. This is my V2, and this is my P2, and this is my final reversible. Now, where would be my final irreversible? ऊपर या नीचे? ध्यान से बताओ, चाहिए तो ये सब ऊपर रीड करो. अपन ने यहाँ पे क्या पढ़ा था? T2 dash is greater than T2 irrespective of anything, expansion या compression. ये तो जनरल रिजल्ट था ना. T2 dash is greater than T2. T2 dash is greater than T2. भले ही वो expansion हो रहा हो या compression हो रहा हो. राइट, तो क्या रहेगा मेरा आंसर? वापस से ऊपर वाला ही पॉइंट रहेगा. ग्रेट, ठीक है. सो आप लोगों को धीरे धीरे समझ में आ रहा है that this will be f dash irreversible. ऑलराइट, चलो थोड़ी सी और मेहनत कराता हूँ आपसे. जस्ट वन मोर बिट, एंड दिस टाइम for the same change in pressure, not taking the same change in volume, but let's say for the same change in pressure. ठीक है, and I don't need two graphs as such. एक ही ग्राफ पे काम चला लेते हैं. Let me put it over here. For the same change in pressure, so let's say now this was F. Let me put it थोड़ा सा ऊपर. This was F reversible. This was the final state of reversible, and we are doing the same change in pressure, like P1 से P2 जा रहे हैं. तो अब V2 डैश जो होगा वो राइट में होगा या लेफ्ट में होगा? Correct. P2 dash will be greater than V2, so this will be somewhere here. F dash irreversible, like V2 dash will be somewhere आगे. Good. ठीक है. So this was about ideal gases. I think we have now a pretty good understanding about ideal gases and their second law calculations, change in entropy. Right. So मैंने आपको जब homework दिया था, like I hope those questions become like really easy for you to work with. Okay, they aren't now a challenge at all. Right. For example, if I gave you certain question like this, ये FBO का ही question था. Right. What will be our answer to this? Right. So you just do NCV ln T2 by T1 plus NR ln V2 by V1. Now what it is saying that gas is compressed to half its volume, यानी कि volume becomes half of what it was initial, and heated to twice the temperature. कोई दिक्कत नहीं है. So this is NCV round 2, and then you can get the answer as D option, right? ठीक है. प्रीवियस वाले क्वेश्चन में कुछ कंफ्यूजन वाली बात नहीं है. यहाँ पे आप ये देखो प्रियांशु, मैंने क्या बोला कि सेम चेंज इन प्रेशर कर रहा है. लाइक P1 से P2 जा रहा हूँ, एक बार रिवर्सिबली जा रहा हूँ और एक बार इरिवर्सिबली जा रहा हूँ. तो फॉर द सेम चेंज इन प्रेशर व्हाट वाज द फाइनल वॉल्यूम, वो मैं कमेंट करने के लिए बोल रहा था. तो रिवर्सिबल मैंने ड्रॉ कर दिया था, इरिवर्सिबल में पूछ रहा था वेदर इट वुड बी टुवर्ड्स द राइट और टुवर्ड्स द लेफ्ट फॉर द सेम चेंज इन pressure. And since T2 dash was greater than T2, so V2 dash has to be greater than V2 for the same change in pressure. As a consequence, ये मेरा point right hand side पे आ गया था. ठीक है? All right. Great. ठीक है. Now let's move on to second law calculations for other systems, right? जैसे आप लोगों ने फर्स्ट लॉ के कैलकुलेशंस करे थे, वैसे ही मैं यहाँ पे फटाफट बात करूंगा सेकेंड लॉ कैलकुलेशंस फॉर solids and liquids, and especially for isobaric heating or cooling of solids and liquids. So what are we looking at? We have an open vessel, say for example इसके अंदर water रखा हुआ है, right? And I am increasing its temperature from T1 to T2, right? What are the two ways in which I can go about? There is reversible and irreversible way, right? I'm heating it. I can go in a reversible manner. What will be a reversible manner? I will be going from T1 to T2. How? Infinitely small changes at a time, keeping system and surrounding in equilibrium with each other, right? What will be my DS system? It will be integral dq by d. What will be my dq? mcp dt. Say because this is a solid, तो उनके लिए स्पेसिफिक हीट दे दिया हुआ सॉलिड या लिक्विड के लिए, MSP. चलेगा? Right? And I'll do the integration. I'll get my answer as MSP ln T2 by T1. This will be my answer for the system. Correct? Acha. What will be my delta S surrounding? It will be minus delta S system. Okay, for the reversible processes, and it will be, I will say, minus MSP ln T2 by T1. Great. Acha, if I did this process in an irreversible manner, how do we visualize this irreversible heating? कैसा बताया था मैंने आपको? I took this system and इसको मैंने एक vast water bath में डाल दिया, oil bath में डाल दिया, which is at a T2 temperature. So my temperature goes directly from T1 to T2. The surrounding is vast, right? And in that case, again, my DS system like it follows the same thing, dq by t, it will come out to be mcp or msp ln t2 by t1. This doesn't change, और होना भी नहीं चाहिए था, because for system we understand it is going from same T1 to T2 temperature, and entropy is a state function, right? Entropy is a state function, and I'm getting the same answer, MSP ln T2 by T1. What about delta S surrounding? In this case, in case of irreversible, it will be minus Q system upon T surrounding, right? So it will be minus MSP delta T upon T surrounding. ये समझ में आया? This will be for isobaric heating or cooling of solids and liquids. Okay. Maybe now, based on this, I can ask you a question. कहाँ गया वो? Right. क्या रहेगा इस क्वेश्चन का आंसर? There is one piece of metal, another identical piece of metal, and they are in contact with each other and isolated from the surroundings. What will be the entropy change of the system? What is the system over here? The blocks combined. That is our system. Correct. Answer निकालो. And इनका heat capacity is से Cp. जो ये metal है, इसका heat capacity is Cp. या sp बोल लो, चलो अगर मास m बोल देंगे. अच्छा, मास भी नहीं दिया हुआ एक्चुअली इनका. मास is equal to m and heat capacity is sp. ये दिया नहीं है क्वेश्चन में, बट मान लो दिया हुआ है. नहीं, why do you say so, श्रेष्ठ? This will be not an adiabatic reversible process, no. ये TC/TH अलग अलग टेम्परेचर्स हैं, एंड करेक्ट. हाँ, तो शौनक तुम्हारा करेक्ट है. रोहित थोड़ा सा गड़बड़ है. like maybe you have typed it correctly or incorrectly, I think. नहीं, साक्षी. So let me first ask you, what will be the final temperature? Let me first ask you that. This is as part A. And then as part B, you can answer what is delta S system. Maybe this will help you then. फाइनल टेम्परेचर तो ठीक है यश, बट आगे का भी बताओ। नहीं नहीं, ऐसे ज्योमेट्रिक मीन क्यों ले रही है वृष्टि? लाइक हीट लॉस्ट इज इक्वल टू हीट गेन होगा ना बस। हाँ राइट। आइशानी, आइशानी, is that, am I pronouncing that correctly? That A is silent or it's just Ishani? अच्छा, okay, Bengali है तो Aishani. My God, your name looks like a Bollywood या इधर बॉम्बे साइड का गाली। Aishani, चल कट ले इधर से। बुरा मत मानना यार, मतलब I'm just joking around. I'm sure it is pronounced in a more wonderful manner in the Bengali language. All right. So yes, final temperature हम लोग कैसे निकालेंगे? Correct. It will be simple calculation. Heat lost is equal to heat gained. Right. तो यहाँ पे जो hot वाला block है वो heat lose करेगा. Right. And magnitude compare कर लेना. Otherwise you will end up having a sign problem. So MSP, this will be TH minus जो भी final temperature होगा. This is the heat lost, and heat gain will be MSP, right? T final minus T cold, right? Since the blocks are identical, your intuitive guess was correct that the final temperature will be T hot plus T cold upon 2. Had they not been identical, then this formula would have helped you. Now, अब because of this, notice करना delta S total. When I say total system, it will be delta S of block 1 plus delta S of block 2. Why? Because entropy is extensive property. ठीक है, state function भी है और extensive property भी है. So like it is additive in nature. I could very well do this. Correct. And now for block 1, notice करना, it will be MSP ln T final by whatever its T initial was, which was TH. And similarly for block 2, it will be MSP ln T final upon whatever its initial temperature was, it was TC. So you get the answer that it will be MSP T final ka square upon TC into TH. And then you substitute what T final was and you will get your answer as MSP. Oh, I forgot ln. TC plus TH का whole square upon 4 TCTH. This is what your final answer would be. समझ में आया? ठीक है. I would prefer to use here SP because these are being or they are getting heated up like under constant pressure conditions. That is what I will be going through. Had they mentioned, like उन्होंने mention करा नहीं है, If they would have mentioned constant volume conditions, then I would have used SV or CV. ठीक है, बट अगर कुछ मेंशन नहीं करेंगे तो जनरली आई वुड बी अज्यूमिंग अंडर कांस्टेंट प्रेशर कंडीशंस. ये क्वेश्चन समझ में आया? किसी को डाउट है इसमें? ऑलराइट. ठीक है देन. सो वी कैन अप्लाई लाइक ऐसे सॉलिड्स एंड लिक्विड्स की हीटिंग कूलिंग के लिए इट्स फेयरली सिंपल टू अप्लाई द सेकंड लॉ. लेट मी अप्लाई सेकंड लॉ. Second law calculations for phase transformations. Right, fusion, vaporization, all of those things that we had studied while discussing the first law also. So इसमें किस तरीके से रहेगा? अब आप यहाँ पे इनफैक्ट ये अपने थोड़े टाइम पहले अप्लाई भी कर ही लिया था. लाइक इफ यू रिमेम्बर इन द लास्ट क्लास मैंने यही एग्जाम्पल लिया था आप लोगों के साथ में. ओ, मैंने यहीं पे लिखना शुरू कर दिया क्या? ये तो आज यहाँ लिखना था. कोई नहीं, चलो मैं बाद में एडजस्ट कर लूँगा. ये लास्ट क्लास में जब हम लोगों ने करेक्ट, you remember I took this example for phase change. Delta H system was delta H fusion upon temperature of system and delta H surrounding was minus delta H fusion upon temperature of the surrounding, and this was the delta H universe. ये याद आया? तो instead of doing the derivation again altogether, this was the derivation that we had done. I will be a little faster over here. ठीक है, so I will put up a note over here saying that we have done the derivation earlier. ये रहा actually my answer. MSP ln TC plus TH का square upon 4 TC TH. So we had derived this in previous lecture. अभी मैं सीधे यहाँ पर आप लोगों के लिए रिजल्ट्स लिख लूँगा. Let's say fusion हो रहा है, right? That means we are going from solid to liquid. अरे, nonsense. So we are going from solid to liquid. In this case, delta S system, or in fact, let me kind of draw a table. Delta S system, delta S surrounding, and if you would want, then we can also put in over here delta S universe, right? So fusion के लिए this will be delta H fusion upon temperature of system. This will be minus delta H fusion upon temperature of surrounding, and delta H fusion minus, or in fact delta H fusion common हो गया, 1 upon T system minus 1 upon T surrounding, right? and this temperature of system was what? The melting point. Okay. And what is it that we had concluded in our previous discussion? अगर सराउंडिंग का टेम्परेचर सिस्टम के टेम्परेचर के बराबर है, मेल्टिंग पॉइंट है, तो व्हाट डू वी से? वी से the system and surrounding are in equilibrium, right? And if temperature of system was more than that of surrounding, right, तो delta H inverse negative हो जाता था, मतलब forward process non spontaneous and backward was spontaneous, right? Okay, then notice करना, if it was say vaporization, लिक्विड से वेपर जाने की बात हो रही है, तो यहाँ पर डेल्टा एच वेपराइजेशन अपॉन टेम्परेचर ऑफ सिस्टम माइनस डेल्टा एच वेपराइजेशन अपॉन टेम्परेचर ऑफ सराउंडिंग। अरे ऐसे क्यों कह रहे हो? तुम लोगों को प्रीवियस लेक्चर ग्रुप पे डाला तो था, व्हाट्सएप ग्रुप पे एडेड नहीं हो गया तुम लोग? ओहो, तो फिर ग्रुप में क्यों नहीं ऐड हो रहे हो? व्हाट, यू गाइस आर अटेंडिंग फॉर द फर्स्ट टाइम? ओह तो तुम लोगों को कुछ समझ में भी आ रहा है क्या? अच्छा, तुम लोगों का थर्मो हो चुका है इसलिए समझ में आ रहा है, ठीक है। हाँ, मतलब एटलीस्ट देन देयर इज सम बैकग्राउंड टू इट, इट इज नॉट अब्रप्ट। हाँ, नहीं नहीं, आई थिंक डिपेंडिंग अपॉन आपका कैसा शेड्यूल रहा होगा। हम्म, ठीक है ठीक है, एनीवेज चलो इसके बारे में थोड़ा बाद में बात करते हैं, ब्रेक के टाइम पे आई माइट टेक सम इनपुट्स फ्रॉम यू, बट एनीवेज लेट मी wrap this up first. 1 upon t system minus 1 upon t surrounding, and here this would be the boiling point, and then you can also talk about sublimation, right? Solid and vapor के बीच में direct interconversion, तो ये क्या हो जाएगा? delta H sublimation upon temperature of system and minus delta H sublimation upon temperature of surrounding. ठीक है, and this can be thought of as the sublimation point temperature. ठीक है, तो ये फेज ट्रांसफॉर्मेशन का था। नाउ इन लेस केसेस ओनली ऐसे डायरेक्ट क्वेश्चन पे बनेगा, बट समटाइम्स यू कैन कम अक्रॉस अ क्वेश्चन विच इज indirect and yet fairly conceptual, fairly easy to grasp and understand. So let me ask you this question straight away. All right, अच्छा क्वेश्चन है एंड थोड़ा लंबा क्वेश्चन है, Take your time, but carefully try to answer. इसमें हीट लॉस्ट इज इक्वल टू हीट गेन का कॉन्सेप्ट लग जाएगा. हीटिंग एंड कूलिंग ऑफ सॉलिड्स के टाइम पर एंट्रोपी चेंज एंड फेज ट्रांसफॉर्मेशन पर एंट्रोपी चेंज, ये सारे कॉन्सेप्ट्स यूज हो जाएंगे. ट्राई करो. नहीं नहीं, होमवर्क नहीं है भाई, अभी करो फटाफट फटाफट. बताओ बताओ किस तरीके से रहेगा इसमें. ओके, सो आई हैव स्टार्टेड गेटिंग सम आंसर्स. पहला वाला क्वेश्चन, उसमें हीट लॉस्ट इज इक्वल टू हीट गेन करना है. करेक्ट. Heat lost by water is equal to heat gained by ice. Now this heat gained by ice has two parts, like temperature का increase होना and melting. Like in fact melting then followed by temperature increase. So यहाँ पर notice करना 9 grams of ice, 9 into 335. This will be what is melting ka heat required, and then that 9 into water जो बन जाएगा 4.18 into final temperature minus 273. ठीक है, temperature being in Kelvin. And heat lost by water, so we had 36 grams of water, same heat capacity, into 50 degree centigrade. 50 degree centigrade मतलब 323 minus T. तो इससे अब आप सॉल्व करोगे. This is change in temperature ना. This was mass into latent heat. This was m sp delta T, and this was also m sp delta T, right? समझ में आया? ग्रेट. सो इससे टेम्परेचर कितना आ जाता है? हैव यू गाइस सॉल्व्ड इट? आई थिंक इससे शायद बी ऑप्शन आंसर आता है. नहीं, बी आता है ना? हाँ, करेक्ट. तो दिस कम्स आउट टू बी सम 296.97 Kelvin. All right, great. Now what about the second part? What will be the change in entropy of ice? So let's see what is happening to ice. So first, ice is going into water, and then it heats up, like to whatever 296.97 Kelvin. Right? तो अब दोनों केस का एंट्रोपी चेंज ऐड अप करना है. यहाँ पर एंट्रोपी चेंज कितना था? Here it will be mass into latent heat of fusion upon the melting point temperature. ठीक है, यूनिट्स का ध्यान रखना है. And here it will be MSP ln T2 by T1. करेक्ट. तो 9 इंटू कितना है ये एंट्रोपी चेंज? 335. 335 upon 273 plus 9 into 4.18 into ln of, ठीक है, कैल्सी वगैरह लग जाएगा इसमें क्योंकि ये ln isn't something that you can solve by yourself. But this should get you the answer for delta S of ice. राइट. एंड ध्यान देना यहाँ पे यूनिट्स ये सब इसी तरीके से है कि जूल पर ग्राम में है तो ये मास ग्राम में ही था. राइट. ये भी जूल पर ग्राम है हीट कैपेसिटी, इसलिए मास 9 ग्राम में था. हैड देयर बीन हीट कैपेसिटीज इन मोल्स एंड ऑल तो फिर अप्रोप्रिएट यूनिट कन्वर्जंस लगेंगे. ठीक है. व्हाट अबाउट डेल्टा एस ऑफ वाटर? It will be just water going from 323 Kelvin to this 296 point कितना था? 97 Kelvin. So यहाँ पर it will be MSP ln T2 by T1. So 36 grams into 4.18 into ln 296.97 upon 323. Of course, this is going to come in negative because temperature decrease हो रहा है, but that's all right. And the fourth part is delta S system, which will be simply the sum of delta S of ice and delta S of water. ठीक है. So it sounds a bit tricky to start with, but it is fairly easy to do. चलेगा आप लोगों को? ये कैसे करा? किसी को कुछ डाउट है इसमें? All right. Great. अच्छा चलो थोड़ा सा एक ट्रिक क्वेश्चन कर लेते हैं आप लोगों के साथ में. Let me see if you are able to understand the trick. All right. ये वाला क्वेश्चन बताओ. नहीं नहीं सोहम, वो पिछले वाले क्वेश्चंस का कैलकुलेशन वाज रियली बैड. वो लॉन में इतने अच्छे वैल्यूज नहीं थे. हाँ, ये वाले क्वेश्चन के बाद आई विल बी गिविंग अ ब्रेक. आप ये वाला क्वेश्चन ट्राई करो, देन आई विल गिव यू गाइस अ ब्रेक. All right, great. We are getting some answers from students. राइट, तो इसमें ट्रिक क्या था? राइट शुभम, राइट तृप्ति, राइट वृष्टि, करेक्ट. एंट्रोपी इज अ स्ट्रेट फंक्शन. ग्रेट. तो इसमें like you get confused in all the jazz that is given in the question. So you have been given helium gas, right? And यहाँ पे बोला जा रहा है that it is originally at 298.15 Kelvin and 1 bar, right? Then it is cooled down to its boiling point temperature, right? It is 4 Kelvin, 1 bar, and then it is condensed to a liquid. So this is some helium liquid at 4 Kelvin, 1 bar, and then it is further cooled where it is some other kind of liquid at 2 Kelvin and 1 bar, and then it vaporizes this helium, like it provides it energy and increases its temperature, and the beam of laser light suddenly vaporizes this liquid phase and brings this helium back to 298.15 Kelvin and 0.5 bar, right? So either you can add these up or just calculate the direct change. The answer should be the same, right? Entropy is a state function. So you need not get bogged down by कि यार हीट कैपेसिटी नहीं दिया है, कैसे करें, क्या करें. तो यहाँ पर आप डेल्टा सीधे निकाल सकते हो. For the same temperature change, this will be n r ln p1 by p2. That's it, and you will get your answer. p1 by p2, p2 by p1 नहीं, यहाँ पे केयरलेस मिस्टेक हो जाएगा. p1 by p2 था ये, तो उसके लिए भी यहाँ पे ये दिया हुआ है. हाँ, तो even after a trick there is another trick, so you shouldn't fall for that. So यहाँ पर nr ln final pressure was 0.5 bar, sorry, final pressure was 0.5 bar, initial pressure was, right? तो मेरा ये पॉजिटिव वाला आंसर करेक्ट रहेगा. ठीक है. ये समझ में आया आप लोगों को? ऑल राइट, ग्रेट. ठीक है, तो अब एक छोटा सा ब्रेक ले लेते हैं. इन द मीन टाइम we can discuss some questions also अगर आपको कुछ डाउट्स एंड ऑल है. अभी तो जो पढ़ा है उसमें ऑफ कोर्स होमवर्क का डिस्कशन मैं अलग से कर लूँगा. रिज्यूम कब करेंगे? 4:55 हो रहा है, तो 5:05, 10 मिनट्स में. हाँ दक्ष. All right, so next chapter what we will do, that is one of the questions that has been the most asked question for the day. Now in terms of the sequence of chapters that goes in here, thermodynamics के बाद में आता है chemical equilibrium. So most likely that would be the chapter. However, डिपेंडिंग अपॉन लाइक आई थिंक थोड़ा सा एक अंडरस्टैंडिंग डेवलप करनी पड़ेगी ऑफ हाउ थिंग्स आर गोइंग इन अदर बैचेस ऑल्सो. हाँ हाँ हाँ, राइट. करेक्ट करेक्ट. सो इन सम बैचेस इक्विलिब्रियम हो चुका है, सम बैचेस में नहीं हुआ है, तो दैट अंडरस्टैंडिंग हैज टू बी टेकन इनटू अकाउंट, and then only there will be a call on the next chapter. क्योंकि थोड़ा थोड़ा mismatch है. If that doesn't happen, then maybe after this next chapter can be chemical kinetics also, which is not done in any other batches. हाँ नहीं, ऑर्गेनिक का ट्रैक आपका अलग रहेगा. ऑर्गेनिक वुड बी डन इन लाइक योर रेस्पेक्टिव सेंटर्स का बैचेस. ऑर्गेनिक में इनफैक्ट इट इज़ बेटर इन केस अगर थोड़े टाइम बाद ऑफलाइन क्लासेस शुरू हो जाती हैं, तो इट इज़ बेटर दैट दैट ट्रैक इज समथिंग विच इज़ डन इन हाउस, लाइक टीचर्स हु आर देयर एट योर respective centers. With that thought process, I think it will be planned. But yeah, even I am to get a clarity on this because multiple locations and multiple batches are sitting in together here. So we'll find out what should be the next chapter. हाँ, थर्मो आज की क्लास में तो कंप्लीट नहीं होगा, बट वी विल ट्राई टू डू इट इन द नेक्स्ट क्लास. ठीक है, मैं अभी ब्रेक के बाद में सेकेंड लॉ अप्लाई करूंगा अब केमिकल रिएक्शंस पर. ठीक है, हमने गैसेस पे, सॉलिड्स एंड लिक्विड्स पे एंड फेज ट्रांसफॉर्मेशंस पे देख लिया है. सो आफ्टर दिस आई विल बी अप्लाइंग सेकेंड लॉ इन केमिकल रिएक्शंस, एंड विद दैट आई विल बी इंट्रोड्यूसिंग द कॉन्सेप्ट ऑफ गिब्स फ्री एनर्जी. Now, once you understand that concept of Gibbs free energy, then second law calculations of reactions will be pretty straightforward. ठीक है, and थोड़ा सा advanced के perspective से, from J advanced perspective, I will try to also talk about Helmholtz free energy. ठीक है, डिपेंड करेगा आप लोगों का कैसा अभी अंडरस्टैंडिंग चल रहा है. पहले तो गिब्स फ्री एनर्जी के ऊपर ही बात करेंगे, फिर उसके बाद में हम लोग हेल्महोल्ट्ज के बारे में देख सकते हैं. एंड देन यस, आई रिमेंबर मैंने आप लोगों को कार्नोट साइकिल के बारे में बोला था दैट आई विल टेक दैट अप फॉर यू, बट वो आज की क्लास में तो नहीं हो पाएगा, मे बी इन द नेक्स्ट क्लास. सो नेक्स्ट क्लास वी शुड बी टारगेटिंग टू कंप्लीट दिस चैप्टर. अच्छा, अपार्ट फ्रॉम दिस one more thing that I had in mind, when should we have a doubt discussion session this week? Let me just check up my schedule. Okay, Thursday, Friday. कल रात को 8 बजे. नहीं, थर्सडे को मेरी एक्चुअली लाइक 9 बजे तक क्लासेस हैं, तो थर्सडे थोड़ा सा मेरा भी टाइड अप है. अभी जो पिछला वाला अपना होमवर्क है उसका डिस्कशन के लिए कल रात को 8 बजे का रखते हैं. आई थिंक दैट वुड बी बेटर. ठीक है, एक बार आ जाने तो सबको ब्रेक के बाद. आई थिंक मेनी स्टूडेंट्स वुड हैव गॉन ऑन द ब्रेक. 5 मिनट बाद यहीं पे रिज्यूम करके आई विल डिस्कस इट एंड क्लोज इट अप. मंडे इतना आगे? नहीं नहीं तेशु, तुम बहुत आगे ले जा रही हो. इतना टाइम नहीं है. अरे आप लोग अभी से इतना क्यों टेंशन ले रहे हो यार सिलेबस को लेकर? सिलेबस होगा, कब होगा? अक्टूबर में होगा। आप लोग मत टेंशन लो अभी इतना इसके बारे में। डेफिनेटली सिलेबस होगा। हाँ, बिकॉज ऑफ द प्रॉब्लम्स दैट केम इन, कई बार बीच में आपको थोड़ा ज़्यादा खींचना पड़ेगा। अच्छा, तो कोलकाता का यू आर सेइंग दैट वन ऑफ द सेंटर्स हैज बीन क्लोज्ड बिकॉज ऑफ दैट। हाँ, बोलो शौनक।
सर एक ये कर रहे हैं अभी तो केवीआई नेक्स्ट मंथ है, उसके लिए सैंपल पेपर्स कर रहे थे, तो उसमें क्वेश्चन था कि अकॉर्डिंग टू राउल्ट्स लॉ व्हाट विल बी द ग्राफ ऑफ वेपर प्रेशर विद कंसंट्रेशन ऑफ सॉल्वेंट, तो वो कैसे करना है?
वेपर प्रेशर का ग्राफ विद कंसंट्रेशन ऑफ सॉल्वेंट।
हाँ ऐसा कुछ क्वेश्चन था।
एक्चुअली ये लिक्विड सॉल्यूशन चैप्टर में रहता है,
ओके सर।
बट इट विल बी अ स्ट्रेट लाइन लाइक इस तरीके का एक्सप्रेशन रहता है वो। मोल फ्रैक्शन से रिलेटेड रहता है। So if y-axis पे you have vapor pressure and x-axis पे you have the mole fraction of solvent, then it will be a straight line. So मतलब वो ठीक है, सिंपली क्वेश्चन होता है, बट वो चैप्टर अलग है, लाइक इट इज इन अ लिक्विड सॉल्यूशन चैप्टर। नहीं, आपको ये जो डाइपोल डाइपोल इंटरैक्शंस है ना, दे आर सपोज्ड टू बी टॉट इन केमिकल बॉन्डिंग चैप्टर। हैव यू गाइस डन दैट चैप्टर केमिकल बॉन्डिंग येट? हाँ, तो यश उसमें आपका चल रहा है, अगर तो उसमें आएगा देयर विल बी अ सेक्शन कॉल्ड एज वंडरवॉल फोर्सेस। उसमें डाइपोल डाइपोल, इंड्यूस डाइपोल, ये सारे टर्म्स एंड इनके इंटरेक्शंस आपके साथ में डिस्कस करे जाएंगे। हाँ, होमवर्क प्राइमरीली बुकलेट में से ही देते हैं। That is something which is the core focus. Then apart from that, I give some TPPs also. अच्छा, ऐसा हुआ है क्या दृष्टि? जो केमिकल बॉन्डिंग पढ़ा रहे हैं उन्होंने बोला कि गैसियस स्टेट जो पढ़ा रहे हैं वो पढ़ाएंगे। ये तो ऐसा विशियस लूप में चला गया। मैं बता दूंगा आप लोगों को, इन केस यू गाइस हैव डन केमिकल बॉन्डिंग, तो आई कैन टेक अप दैट टॉपिक आल्सो ऑफ van der Waals forces, जिसमें we talk about these हम्म। हाँ, मतलब मुझे एक्चुअली इस चीज़ का बैकग्राउंड नहीं है सोहम, लाइक हाउ थिंग्स हैपेंड एट द कोलकाता सेंटर, बट या मतलब टुडे इन फैक्ट दिस इज अ न्यू पीस ऑफ इंफॉर्मेशन फॉर मी आल्सो, सो आई विल try and understand that what is the background regarding this. ऐसा लग रहा है बहुत टेंशन में हो आप लोग, लाइक एकदम ऐसे एग्जिस्टेंशियल क्वेश्चंस आ रहे हैं आप लोगों के, हमारा क्या होगा, हम ऑर्गेनिक की टेस्ट में कैसे करेंगे। आई कैन सिंपथाइज कि हुआ क्या है वहां पर, मुझे भी एक्चुअली आइडिया नहीं है। ठीक है, आई थिंक नहीं नहीं, यहाँ पर ऑर्गेनिक चल रहा है, इनफैक्ट जीओसी चल रहा है इन बॉम्बे एंड एसोसिएटेड बैचेस। नहीं नहीं नहीं, आइसोमेरिज्म तो आया ही नहीं है अभी, अभी तो जीओसी चल रहा है, जीओसी के बाद आइसोमेरिज्म आएगा ना। चलो, ऑल राइट, आई होप मोस्ट ऑफ द स्टूडेंट्स आर बैक फ्रॉम द ब्रेक। So now let's focus back on thermodynamics and continuing on the same direction. Like अभी जैसे अपन लोग देख रहे थे, हम लोग सेकेंड लॉ कैलकुलेशंस ऑब्जर्व कर रहे थे फेस ट्रांसफॉर्मेशन के बारे में. So let's put up the next heading. Second law calculations or chemical reactions. ठीक है, सो अब यहाँ पर आप ऑब्जर्व करना, when we'll be talking about these second law calculations for chemical reactions. तो while discussing or applying second law on chemical reactions, we would be introducing a new thermodynamic property called as Gibbs free energy. Now, why do we do that? Why do we introduce this new thermodynamic term called Gibbs free energy? Well, primary reason would be out of convenience. That will be the primary reason. Now, what will that convenience be? You will be able to appreciate that convenience, but maybe आफ्टर सम टाइम. जैसे आपको याद हो तो स्टार्टिंग में मैंने एंथैल्पी के बारे में आपको बताया था, that there was this thermodynamic term called enthalpy that was introduced, and that was again introduced from the point of view of convenience only. So starting में आप लोगों को थोड़ा दिक्कत आया था to grasp what this concept was exactly. However, once we started applying it, then you understood that this being a state function and an extensive property comes out to be very handy. Because of it, we can calculate energy exchanges happening in certain reactions which might not be even practically doable. हाँ बोलो पार्थ. अच्छा, ऐसे हो गया था. सिमिलरली वैसे ही अब यहाँ पर आप नोटिस करो कि हम लोग ये एक और थर्मोडायनेमिक प्रॉपर्टी है गिब्स फ्री एनर्जी, इसको डिफाइन करेंगे, डिस्क्राइब करेंगे एंड यूज करेंगे as it helps us in understanding the condition of spontaneity and the concept of chemical equilibrium. ठीक है, तो इसका convenience, इसका help is something which you will be able to understand after some time. Now, notice करना, while we are going to be discussing chemical reactions, it will be extremely important to remember that our discussion will be about chemical reactions under constant pressure comma temperature conditions. So our scope of discussion has been limited to constant pressure temperature conditions, and in that we are going to define Gibbs free energy, that term called G. So अब आप यहाँ पे observe करना. We'll start with the understanding of second law of thermodynamics. For a spontaneous process, we had studied second law of thermodynamics, that delta S universe, change in entropy of universe, has to be greater than 0. Delta S system plus delta S surrounding has to be greater than 0. Now this delta S surrounding can be written as minus Q system upon T surroundings. अब आप यहाँ पे नोटिस करना, for a reaction under constant temperature comma pressure condition, like Q can be written as delta H, like heat exchange under constant pressure condition is delta H, and we can also write, because constant temperature conditions per temperature of surrounding is the temperature of the system also, right? So it is like saying, for example, say you had certain reactants, right? CH4 and O2, right, under room temperature pressure condition, ठीक है, under room temperature pressure condition undergo combustion, right? जो भी heat release होना होता है वो हो जाता है, and the final products, what were the final products? CO2 and H2O are also at room temperature comma pressure conditions, and इसके ऊपर अब हम analysis का discussion कर रहे हैं, like इसके ऊपर हम analysis कर रहे हैं, ठीक है? That is what we are trying to understand. So by substituting these in our above equation, we get something like this as the condition of spontaneity. The delta S system minus delta H system upon T is greater than 0. ठीक है? Now, having this situation in front of us, notice करना, for further simplification, of condition of spontaneity, we, or in fact for condition of spontaneity of reaction under constant temperature pressure condition, ठीक है? मैं बार बार रिपीट करूंगा ये ताकि आपके दिमाग में एम्बेड हो, that it is under constant temperature pressure conditions that we are defining So for simplification of condition of spontaneity of reaction under constant temperature pressure condition, we define a new thermodynamic variable, a new thermodynamic property called Gibbs free energy. And we give this a symbol G. Now, how are we defining this thermodynamic property? यहाँ पे notice करना G is equal to H minus Ts. Now, this is also not by luck or by chance that G is equal to H minus Ts लिख दिया है. G is equal to H minus Ts is a deliberately designed thermodynamic property which in itself talks about the second law of thermodynamics. किस तरीके से आप यहाँ पे नोटिस करना, what was H? If you remember, it was enthalpy, or in other words, we define this as the net heat content, or I should in fact say total. I should not use the word net, otherwise you might get confused. This was the total heat content of system under constant pressure conditions. Now, अब आप यहाँ पे नोटिस करना that second law of thermodynamics का एक फिजिक्स में इंटरप्रिटेशन रहता है that total heat content, like total heat, cannot be converted into work. Right? Total heat, like you can't design a thermodynamic cycle which utilizes the entire heat content and does work out of it. There is some part which is unavailable, which cannot be used for doing work. This is something which is demonstrated in a simple manner, saying that, we have a heat source and we have a heat sink, right? So spontaneously heat is going to travel from hot to cold region, and we can use up that heat. This transfer of heat can be used up via a thermodynamic cycle to do some work. However, the entire heat supplied cannot be used to do work. There is some part that gets dissipated. There is some part of the heat that gets dissipated to the sink. So Qs will never be equal to W. In fact, W will be less than Qs. This is an interpretation of second law of thermodynamics that comes in physics from a thermodynamic cycle perspective. तो उसी तरीके से और उसी लाइंस पर इनफैक्ट आई वुड से ये थर्मोडायनेमिक प्रॉपर्टी डिजाइन करी जाती है which is called as Gibbs free energy, that the total heat content of the system, ठीक है, which is called this H, this cannot be used completely for doing work. There is some part which is unavailable. This T into S term represents the unavailable energy for useful work. And the difference between the two, H minus Ts, total minus unavailable, this is what is called as available or free energy for useful work. So this is the way in which you can think that this thermodynamic property called Gibbs free energy is defined or designed as G is equal to H minus Ts. Now, how it comes as a help in our condition of spontaneity, how it helps in this simplification of condition of spontaneity, यहाँ पे मैं आता हूँ. Give me just couple of more steps. Please note H, T, S, they are all state functions, right? So G or Gibbs free energy is also a state function. And an extensive property. Please note, हम लोग एंथैल्पी की एब्सोल्यूट वैल्यू नहीं निकाल पाते थे, राइट? सो उसी तरीके से we'll make a comment over here that absolute value of G cannot be calculated. However, what comes of use is the change in Gibbs free energy. Right, so the absolute value of G cannot be determined. The change in Gibbs free energy, this can be written and understood, especially under constant temperature conditions also. Can be written as delta G is equal to delta H minus constant temperature conditions बोला है तो T बाहर आ जाएगा, delta S, ठीक है, under constant temperature conditions. Now this is something which you can now substitute back into the condition of spontaneity. ठीक है, यहाँ पे notice करना, substituting this result in condition of spontaneity. So what are we getting? ध्यान से नोटिस करना, डेल्टा एस यूनिवर्स हम लोगों ने अभी तक सिंप्लीफाई कर लिया था. इट वाज कमिंग आउट टू बी डेल्टा एस सिस्टम minus delta H system upon T, which you can further rewrite as minus delta G system upon T. Like if you take this common, like T in the numerator and then substitute this. And what was the condition of spontaneity? That delta S universe has to be greater than 0. And from here, if I was to write it in terms of delta G and just focusing on the system, okay, not focusing on the surrounding, delta G system is less than 0. That becomes your condition of spontaneity. Now, the convenience which you can now appreciate was that when we were talking about a spontaneous process, it was both system and surrounding that we had to do the calculations for. So we eliminated that by writing delta S surrounding as minus Q system by T surrounding. Now, under constant temperature pressure conditions, ठीक है, वैसे ये जो Q system है, this is a path function. Okay, this is a path function, so this condition is still not convenient for us. So what we do is we then talk about chemical reactions under constant pressure comma temperature conditions and then try to bring it down under this situation. That Q system को delta H and T के form में यहाँ पे replace कर दिया. However, this is still like ठीक है, यहाँ तक भी ठीक है, अभी भी you could put this as a condition of spontaneity. However, we wanted further simplification, we wanted further ease of describing spontaneity in terms of just one thermodynamic variable with a chemical reaction under constant temperature pressure conditions. And this is where we introduced Gibbs free energy as this thermodynamic property defined as G is equal to H minus Ts. Okay, although it may seem like कि deliberately किया है, however इसके पीछे भी second law का interpretation है which I spoke to you about, and this then helps us simplify the condition of spontaneity as delta G system to be less than 0. So अब notice करना यहाँ पर when I will be talking about chemical reactions and asking about their spontaneity and non-spontaneity, it will be using this thermodynamic term delta G subject to reaction under constant temperature pressure conditions. Now इसके साथ में notice करना कुछ कुछ terms रहते हैं. So delta G less than 0, right? This is read as exoergic. ठीक है, जैसे exothermic होता था delta H less than 0, वैसे ही delta G less than 0 is read as exoergic. This means process is spontaneous. If delta G is greater than 0, we use the term endoergic, and what it means is that the process is non-spontaneous. Non-spontaneous in the forward direction, spontaneous in the backward direction. And if delta G is equal to 0, right, then we understand this as the condition of equilibrium. ठीक है, हाँ, T is the temperature at which we were analyzing the reaction. T and P conditions, these are again I will highlight under constant, ये क्योंकि बहुत बार बच्चे भूल जाते हैं, under constant temperature pressure conditions. right? Which is actually the most common condition in which we observe processes around us. ठीक है, थोड़ा टाइम मिलेगा बाद में, तो आई एम गोइंग टू ऑल्सो टॉक अबाउट कॉन्स्टेंट v comma t condition, in which I am going to talk about a variable called as a, Helmholtz free energy. ठीक है, हम इसको डिफाइन करेंगे as u minus ts, and then the condition of spontaneity will be in terms of this Helmholtz free energy. तो वो हम लोग बात करेंगे, बट आफ्टर अंडरस्टैंडिंग द गिब्स फ्री एनर्जी का एप्लीकेशंस. ठीक है, तो इतना पार्ट समझ में आया आप लोगों को गिब्स फ्री एनर्जी का? इसमें किसी को कुछ डाउट है? एनीथिंग यू वुड वांट टू आस्क एंड अंडरस्टैंड? अच्छा, having said this, there are two very important aspects that go along with the Gibbs free energy and its discussion. ठीक है, that is an important note I would put here. Certain exergic reactions. ठीक है, अगर मुझे अब कोई रिएक्शन है जो होगा या नहीं होगा, ठीक है, वो अगर जज करना है, तो दिस विल बी माय वे of thermodynamically assessing whether the reaction will be feasible or not. अगर कोई रिएक्शन है, उसका डेल्टा G comes out to be less than 0, then that reaction is thermodynamically feasible. It will happen. If the delta G is greater than 0, then that reaction is not going to happen under the conditions of temperature and pressure that have been described. अब नोटिस करना, ठीक है, this is note number 1, I should say. ठीक है, this is extremely important. Certain exergic reaction, although thermodynamically feasible, or we use the word spontaneous, that is, they will happen by themselves, by itself. Do not occur in real life. For example, conversion of diamond to graphite under room temperature pressure conditions. Okay, this is one of the classic examples to emphasize this point. Is spontaneous, is exergic, that is delta G less than 0. इसकी जब कैलकुलेशन करी जाती है, राइट, चेंज इन गिब्स फ्री एनर्जी की, तो दिस कम्स आउट लाइक कार्बन डायमंड टू कार्बन ग्रेफाइट is an exergic reaction. That is, according to thermodynamics, आपके पास रखा हुआ डायमंड बाय इटसेल्फ ग्रेफाइट में कन्वर्ट हो जाना चाहिए. However, we do not find that to be happening in real life. Reason being, right? Can anyone tell me the reason? Has someone heard about it? It is right, chemical kinetics. In fact, graphite is the most stable form of carbon. So diamond should spontaneously convert into graphite. However, we do not see this happening in real life. And the reason is kinetics, because the rate of this conversion, डायमंड से ग्रेफाइट जाने का जो रेट है, that is so slow that practically we don't see that change happening. Thermodynamically it is feasible, but in our lifetime, like in fact in much larger scale of lifetime, we do not see such reaction, conversion of diamond to graphite, not happening. We would require the kinetics, the rate of that reaction to be significant to see that change happening. ठीक है, तो यहां पर let me complete this statement. Notice करना, certain exergic reactions, although thermodynamic feasible or spontaneous, do not occur in real life because their rate or kinetics, okay, this is another branch of chemistry in itself, is very slow. They are extremely slow and we do not see them happening. So this is something of a question which you might yourself will come across. आप थोड़े टाइम में खुद ही ये डाउट मुझसे पूछोगे after some time, because you might say that sir, हम लोग जब analysis कर रहे हैं, for many reactions it is coming that delta G is less than 0, but we don't see such reactions happening in real life. So the reason behind those is actually that under those conditions, the rate or the kinetics of the reactions will be very slow. For them to be happening to an appreciable extent, we might have to use certain catalysts or certain methods to overcome activation barrier and get those reactions going at a much faster rate. Achha, another important note which I would like to highlight over here, जिससे कई बार स्टूडेंट्स कंफ्यूज रहते हैं, ठीक है, तो यहां पर नोटिस करना, स्टैंडर्ड गिब्स फ्री एनर्जी चेंज. So this is also something of an important point to differentiate. किस तरीके से आप यहाँ पे नोटिस करना, ध्यान से समझना. We will represent this symbol using delta G, and क्योंकि standard है तो we will put in over a not symbol over here. So similar to how we had defined in thermochemistry, delta H naught, those standard conditions are also what we are using over here. नोटिस करना किस तरीके से, फॉर अ रिएक्शन, ठीक है, फॉर अ रिएक्शन से रिएक्टेंट गोज टू प्रोडक्ट्स, ठीक है, फॉर अ रिएक्शन अंडर any condition, any general condition, how do we write? Delta G will be Gibbs free energy of products minus Gibbs free energy of reactants. However, we face the same dilemma which we had earlier. What was that dilemma? एंथैल्पी के टाइम पे हमने ये फेस किया था कि नहीं किया था, याद है कि नहीं याद है? Absolute value of G of a substance cannot be calculated, right? So we are kind of stuck with this कि भाई ये तो तरीका नहीं चलेगा to compute the change in Gibbs free energy, like delta G of the reaction अगर मुझे निकालना है तो मैं ऐसे तो नहीं कर सकता. In fact, if we weren't able to get this thing done, तो हम लोगों ने बोला था कि let's talk about standard conditions and then take reference. So that's what we do. यहाँ पर notice करना, for a reaction under standard condition, right? What is meant by standard condition? ये हम लोग पहले डिफाइन कर चुके हैं. I had spoken about this. Gases हैं तो partial pressure 1 bar. Liquids and solids are pure under pressure 1 bar. If you have a dissolved species, then its concentration, molar concentration to be 1 molar under a pressure of 1 bar. Temperature can be anything, but if nothing is specified, then what do we take the temperature to be? It is 298 Kelvin. So we had talked about what standard condition was. So for a reaction under standard condition, right, reactant goes to product, then the change in the Gibbs free energy of the reaction is called as delta G naught. Right, delta G naught of the reaction. And it will be standard Gibbs free energy of products minus standard Gibbs free energy of reactants. And even like these standard values, but absolute values cannot be calculated. So we define a reference. किस तरीके से? Like how we did for enthalpy of formation. So यहाँ पर notice करना, thus we define a reference, that is standard Gibbs free energy of formation of elements and compounds, such that, what was the way in which we do that? ध्यान से ऑब्जर्व करना, delta G naught reaction will be equal to sum of Gibbs free energy of formation of its products multiplied by their stoichiometric coefficients minus sum of Gibbs free energy of formation, standard Gibbs free energy of formation of reactants. Okay, let me put capital R over here. Multiplied by their stoichiometric coefficients to get the standard Gibbs free energy of a standard Gibbs free energy change of a reaction. राइट, मैं एक बार यहाँ पर डिस्क्राइब कर लेता हूँ ईच टर्म को अच्छे से हम लोग समझ लेते हैं. व्हाट इज डेल्टा जी नॉट रिएक्शन? दिस इज द स्टैंडर्ड गिब्स फ्री एनर्जी change of a reaction, right? What is this new representing? This is representing the stoichiometric coefficient. Like, I'll just use the word coefficient. What did this represent? Standard Gibbs free energy of formation of products. And this was standard Gibbs free energy of formation of reactants. ठीक है, again multiplied by their respective coefficient. So with this, like the reference that is defined, that is the standard Gibbs free energy of formation of elements and compounds, we are able to then talk about the standard Gibbs free energy of reactions or change in Gibbs free energy of reactions. ठीक है, नोटिस करना डेल्टा GF naught Gibbs free energy of formation of elements is assigned to be 0 in their most stable naturally occurring form. क्या क्या था ये? जैसे कार्बन के लिए इट वाज कार्बन ग्रेफाइट, हाइड्रोजन के लिए इट विल बी हाइड्रोजन गैस, ऑक्सीजन के लिए इट विल बी ऑक्सीजन गैस, ब्रोमीन के लिए इट वाज ब्रोमीन लिक्विड, सल्फर के लिए कौन सा फॉर्म था? Which allotropic form of sulfur was this? Rhombic. फॉस्फोरस के लिए फॉस्फोरस रेड व्हाइट ब्लैक कौन सा था? करेक्ट, फॉस्फोरस व्हाइट. तो उनके लिए ये गिब्स फ्री एनर्जी ऑफ फॉर्मेशन 0 असाइन करते हैं. एंड डेल्टा GF नॉट Gibbs free energy of formation of compounds. How is it defined? Is the free energy change of 1 mole of compound formed from its constituent elements under standard state. ठीक है, तो इस तरीके से हम लोग इस गिब्स फ्री एनर्जी के बारे में बात करते हैं, द स्टैंडर्ड गिब्स फ्री एनर्जी। ठीक है, अब ध्यान से नोटिस करना, डेल्टा जी एंड डेल्टा जी नॉट के बीच में डिफरेंस है। व्हाट इज डेल्टा जी? Gibbs free energy change under any given condition. Gibbs free energy change under any condition. So let's say ये reaction है N2 plus 3H2 is giving 2NH3. ठीक है, any condition का मतलब क्या हो गया? Like I don't care, this can be P1 bar, this can be P2 bar, their partial pressures, this can be P3 bar. ठीक है, under those conditions of any टेम्परेचर प्रेशर कंडीशंस, जो भी मेरा गिब्स फ्री एनर्जी का चेंज आएगा उसको मैं डेल्टा जी बोलूंगा, सिर्फ डेल्टा जी ऑफ द रिएक्शन, गिब्स फ्री एनर्जी चेंज अंडर स्टैंडर्ड कंडीशंस। व्हाट इज डेल्टा जी नॉट रिएक्शन? Do you understand this now? What is delta G naught reaction? This will be Gibbs free energy change under standard conditions. What were the standard conditions? For this reaction, the standard conditions would be partial pressure of a gas to be 1 bar. इसका partial pressure भी 1 bar, इसका partial pressure भी 1 bar, इसका partial pressure भी 1 bar. ठीक है, and if temperature is not mentioned, then we take it to be 298 Kelvin. ठीक है, so keeping this in mind, ध्यान से नोटिस करना आप, the condition of spontaneity of a reaction is as per delta G and not delta G naught. ठीक है, दिस इज द इंपॉर्टेंट कंक्लूजन जिस पर काफी बार बच्चे कंफ्यूज होते रहते हैं. That for a reaction, if I have to judge whether it will be spontaneous or non-spontaneous, like spontaneous in forward direction or non-spontaneous in backward direction, or vice versa, or in fact the condition of equilibrium, then it has to be judged via delta G. ठीक है, not delta G naught. Delta G naught is the Gibbs free energy under a particular condition, that is a standard condition. That is what delta G naught is about. It is what we use to define references. However, किसी reaction का spontaneity non spontaneity judge करना है तो it has to be as per delta G. not delta G naught. ठीक है, like similar to this, like I can say that what do we mean by condition of equilibrium for a reaction? Condition of equilibrium is delta G equal to 0, not delta G naught equal to 0. ठीक है, so that is where you need to be extra cautious. There is an important relationship, ठीक है, ऑल्दो इस चैप्टर में इतना ही नहीं यूज होगा, ये केमिकल इक्विलिब्रियम चैप्टर में यूज होता है. देयर इज एन इंपॉर्टेंट relationship between delta G and delta G naught, which is written in the following way, that delta G is equal to delta G naught plus RT ln Q. What is this term Q? This term Q represents, ठीक है, in a very trivial manner, very simplified manner में आपको मैं बता रहा हूँ ये, that this term Q, this is called as reaction quotient. ठीक है, आप लोगों ने जिन्होंने केमिकल इक्विलिब्रियम पढ़ लिया है तो you might have come across this term called as reaction quotient. It represents the participation, ठीक है, मैं इसके पीछे का एक सिंपल या सिंप्लीफाइड मीनिंग बता रहा हूँ. It represents the participation of reaction species, ठीक है, RXN is short for reaction. So this represents participation of reaction species in the reaction relative to their standard state. Right, so for example, जैसा भी मैंने यहाँ पे ऊपर आपको ये एग्जांपल दिया, that this is the reaction under standard state, whereas this is the reaction under non-standard state. Right, what do I mean by standard state? N2 का partial pressure 1, H2 का partial pressure 1, NH3 का partial pressure 1 bar. That is what the standard state is. But in general, in life, when we analyze this reaction, it is nowhere necessary that these partial pressures are to be 1 bar. They can be anything, P1, P2, P3. Now, under those conditions of pressure P1, P2, P3, how these species will be participating in the reaction, how their participation would be as compared to their standard state, is what is mentioned in this term called as Q. And that then gives us the Gibbs free energy change under non-standard conditions. ठीक है, हाँ, अब जिन लोगों ने केमिकल इक्विलिब्रियम पढ़ लिया है, ठीक है, तो वहां पर ये चीज हो जाती है. ठीक है, जिन लोगों ने केमिकल इक्विलिब्रियम पढ़ लिया है, ठीक है, मैं उनके लिए जस्ट लिख रहा हूं ये, एट इक्विलिब्रियम डेल्टा जी इज 0 एंड क्यू इज के. ठीक है, तो नाउ यू गाइस विल बी एबल टू बेटर रिलेट टू दिस. ठीक है, जिन्होंने नहीं पढ़ा है, they will anyways get to know this when they will be studying chemical equilibrium. ठीक है, all right. So this was introducing, you can say, second law of thermodynamics. for chemical reactions. Now, how it is to be applied, how it is to be understood, ठीक है, उसके लिए I would be taking you through certain questions from the booklet itself. ठीक है, but अभी तो अपना टाइम हो चुका है for the current lecture. So मैं यहीं से फिर पिक करता हूँ so that we have a continuity. आज के लिए यहाँ पर एक लॉजिकल ब्रेक लगाया जा सकता है wherein we have introduced this term called as Gibbs free energy. अब इसको क्वेश्चंस में कैसे यूज करेंगे वो मैं आपको नेक्स्ट क्लास में बताऊंगा. अभी तक जो मैंने डिस्कस किया है उसमें एनी क्वेश्चंस, एनी डाउट्स दैट यू गाइस हैव? All right. So then tomorrow, ठीक है, I am keeping 8 to 10 a doubt discussion. ठीक है, एज अ इम्पॉर्टेंट नोट मैं यहाँ पर मेंशन कर देता हूँ. नहीं, वेडनेसडे 8 PM to 10 PM. ठीक है, we'll have a doubt session of the homework that I had shared with you guys. Right, क्या होमवर्क था? ये होमवर्क का, ठीक है, let me in fact put it over there. हाँ, आज जो मैंने पढ़ा है उसका होमवर्क मैं ग्रुप पे शेयर कर दूंगा आप लोगों के साथ में. व्हाट ऑल क्वेश्चंस यू कैन डू, एंड आई विल आल्सो शेयर द लिंक ऑफ द ग्रुप. जैसे आज आपको इसका जूम मीटिंग का लिंक मिला, उसी तरीके से उन्हीं ग्रुप्स पे आई विल शेयर द व्हाट्सएप ग्रुप का लिंक आल्सो, एंड यू गाइस कैन ज्वाइन इन. जस्ट वन कंसर्न वुड बी कि शायद ग्रुप्स फुल नहीं हो गए. हाँ, मैं मेडिकल वाला ग्रुप का लिंक आप लोगों के साथ में शेयर कर दूंगा. इंजीनियरिंग वाले ग्रुप का आई थिंक वो फुल हो चुका है. ठीक है, तो मैं उसमें मेडिकल वाले का, तो आई एम शेयरिंग द सेम कंटेंट ओवर बोथ द ग्रुप्स ओनली, एंड इफ दैट डजंट वर्क देन आई विल हैव टू क्रिएट अनदर ग्रुप. ठीक है, चलो, ऑल राइट देन. Any questions guys? Anything else you would want to understand? हाँ, एक दो questions पूछे हैं. किसने? वृष्टि ने एक पूछा है. Is this the same endoergic energy used for excitation of electrons in excitation theory of chemical bonding? No, not really, Vrishti. Like when we talk about excitation of electrons, that happens especially in case of expanded octet compounds. Like for example, you have to form PF5, right? PF3 plus F2 से PF5 बनाने का है, right? तो इस रिएक्शन में जो डेल्टा जी होगा, ठीक है, that will be something which will be because of overall what changes are going to happen. ठीक है, क्या क्या चेंजेस हो रहे होंगे यहाँ पर? F और F के बीच का बॉन्ड ब्रेक हो रहा होगा, P और F के बीच में bonds form कर रहे होंगे, right? तो they will be captured in this delta H. Then there will be change in entropy that will be happening also. Like यहाँ पर 2 moles of gas से 1 mole of gas बन रहा है, तो that entropy change also gets taken into account, and उसका net जो result मेरा आएगा, that is what is going to give me the Gibbs free energy. अब during this reaction, excitation of electrons is a very small part that also happens. Like phosphorus के electrons ground state से excite हो जाएंगे. So that is one of the things that happen during this entire reaction. ठीक है. Then इसके अलावा I think हाँ, ये आगाज ने भी एक डाउट पूछा था. क्या था आगाज? You wanted to actually go through this definition once more. हाँ हाँ, okay. So while we were talking about this Gibbs free energy H minus Ts, right? तो इसमें आप नोटिस करना. So let me in fact give you a forward looking example, आगाज. हाँ, let me in fact give you a forward looking example. So इलेक्ट्रोकेमिस्ट्री चैप्टर में आप ये कॉन्सेप्ट सीखोगे, एंड ऑलरेडी आपको ये कॉन्सेप्ट पता होगा that through chemical reactions I can do electrical work. Have you come across this in real life? Of course you have. Like आपके phone की बैटरी, आपके लैपटॉप की बैटरी, like all the batteries around you, they work on this principle that उनके अंदर कुछ ना कुछ chemical reaction हो रहा है जिससे electrical work होता है. ठीक है. Now the thing is that this delta H is not actually equal to the electrical work. You might say कि chemical reaction है, right? And उस chemical reaction से जो heat release हो रही होगी, right? Is that what is going into electrical work? The answer is no. This entire delta H, this entire delta H term, this is the net heat content that is available with the reaction under constant pressure conditions. But this is not something which does the or which is equal to the electrical work that we get out of that reaction. In fact, what we do get, like theoretically speaking, it is delta G, which is the available work that can be, or available free energy that gets converted into electrical work. So यहाँ पर notice करना that this delta H, or I should say, like if not talking about a reaction, any system that you have, उसका enthalpy content cannot be completed into or cannot be completely converted into work. There is some part which is unavailable, and that unavailable part is something which is related to entropy. In fact, entropy is sometimes also defined as a measure of unavailable energy. ठीक है. Entropy is not energy. Entropy का dimensions अलग है. It is joule per Kelvin, but it is talked about as a measure of unavailable energy that cannot be used for doing work. So total minus unavailable is what is called as available for doing useful work, and this is under constant pressure conditions is called as Gibbs free energy. हाँ बोलो यश.
सर फिर वो अनअवेलेबल एनर्जी आपकी कहाँ है?
Unavailable energy जाती कहीं नहीं है. It is something which we cannot extract for doing work. Like इसका एक simplified understanding इस फॉर्म में, like जैसे मैंने आपको बताया ना, जैसे मैंने बैटरी वाला आपको एग्जांपल दिया, ठीक है, ये एक एग्जांपल हो गया. अनदर एग्जांपल विच इज गिवन, ठीक है, ये बैटरी वाला तो थोड़ा केमिस्ट्री रिलेटेड एग्जांपल हो गया. फिजिक्स के पर्सपेक्टिव से, like the example that is generally given is this way, that you have, say, a heat source, high temperature, and a heat sinks at a lower temperature, right? And you have some method, some process designed to take up heat from this hot region, from this source, and do some work for you. ठीक है? So what we understand is that this heat supplied cannot be completely converted into work. There is some part which gets dissipated into the sink, into the surroundings, into the heat sink. Like this is the simplest way of understanding it. So whenever, let's say, we are talking about conversion of these forms of energy, whenever we are talking about a system being used to do certain work, right? In that case, what the second law of thermodynamics does tell us is also that the heat supplied, यहाँ पर नोटिस करना, ये साइकिल्स रहती हैं, ठीक है. ये जो अंदर है, ये जो प्रोसेस के बारे में बात करूंगा, इनको साइकिल्स बोलेंगे, ताकि चेंज इन इंटरनल एनर्जी एंड ऑल ये सब जीरो रहे, ठीक है. तो ये जो हीट सप्लाइड है, दिस कैन नॉट बी completely used in doing work. There is some part which remains unavailable, which gets dissipated into the sink, and that is the reason what we say perpetual machines are not possible. ठीक है, इसका प्रूफ भी रहता है. इसका प्रूफ एक्चुअली प्रूफ बाय कॉन्ट्रडिक्शन होता है, जिसमें व्हाट दे डू इज दैट दे से कि चलो मान लेते हैं कि entire heat supplied gets converted into work and there is no heat released into the cold region. ठीक है, ऐसा मान लेते हैं कि ऐसा हो रहा है. तो अब इसका रिवर्स अगर मैं डिजाइन कर दूं, तो दैट entire work supplied can be used to transfer into heat, and by using that, ठीक है, अभी मेरे को इसका काइंड ऑफ आपके लिए फिर पूरा डायग्राम बनाना पड़ेगा. By using that statement कि if we assume that entire heat supplied is converted into work, we end up, ठीक है, we do design a process in such a manner that we end up with this argument that heat flows spontaneously from cold to hot region, which is not something that we observe. तो उसके पीछे ये स्टेटमेंट आता है, which is, as I said, कि आपको फिजिक्स के पर्सपेक्टिव से ज्यादा बताया जाता है, that this heat supplied is not completely converted into work. ठीक है. हाँ हाँ, वो उसमें एफिशिएंसी के पॉइंट ऑफ व्यू से बोलते हैं. मैं आपके साथ में एक बार डिस्कस करूंगा जब कार्नोट साइकिल के बारे में बात कर रहा हूँ. बट हाँ, अभी फ्रॉम अ बेसिक पर्सपेक्टिव, this would be the interpretation that we'll be working with, the Gibbs free energy. हाँ, 100% efficiency is not possible. Correct. ठीक है. All right. Any other doubts, guys? Any other questions that you would want to ask or understand? ठीक है, तो फिर मैं रिकॉर्डिंग एंड ये नोट्स आप लोगों के साथ में शेयर कर दूंगा एंड आई विल ऑल्सो डिस्कस द होमवर्क टुमारो 8 PM to 10 PM. ठीक है. Then we are going to move on to this thing also. Application of Gibbs free energy on chemical reactions. ठीक है. चलो, thank you guys. Take care.